From the outside, an HVDC converter station looks like a traditional power facility. Steel structures, transformers, reactors, and valves. But inside, the reality is very different. An HVDC converter station is a tightly integrated cyber-physical system, where software, communication, and control logic are just as critical as electrical equipment. If we want to understand cyber risks in HVDC, we first need to understand how a converter station actually works. Modern HVDC converter stations use a layered control architecture. Each layer has a specific role, and each layer introduces its own cyber exposure. Typical control layers include station control level, converter and valve control level, protection systems, communication networks, and engineering and maintenance access. Cyber risks rarely come from a single component. They emerge from interactions between layers. The station control system is responsible for power flow control, operating modes, coordination with other HVDC stations, and interface with SCADA and national control centers. It has system-wide visibility, it can influence large power transfers, and it often supports remote operation. If this layer is compromised, power references can be manipulated, control modes can be changed, and system stability can be affected without any physical damage. This is a high-impact layer, even if access appears indirect. Below the station control level lies the converter and valve control system. This includes pulse generation, valve firing logic, current and voltage regulation, and fast inner control loops. These systems operate on real-time controllers, deterministic communication, and extremely tight timing constraints. Small signal manipulation can cause large system effects, cyber incidents may look like normal control instability, and detection is extremely difficult. Even minor delays, false measurements, or timing errors can destabilize converter operation. HVDC protection systems are designed to detect faults within milliseconds, trigger blocking or isolation actions, and protect valves and critical equipment. They rely on high-speed measurements, communication-assisted protection schemes, and precise coordination between stations. Traditionally, protection systems were isolated. Today, they are increasingly networked, software configurable, and integrated with digital communication. The challenge is clear. Security must not slow protection performance. Balancing speed and cybersecurity is one of the hardest problems in HVDC design. Modern HVDC stations depend heavily on fiber optic Ethernet networks, redundant communication paths, and time-synchronized data exchange. Communication supports control coordination, differential and line protection, and monitoring and diagnostics. Cyber risks can appear from misconfigured switches or routers, unsecured gateways, or shared networks with non-critical systems. In many cases, the communication network becomes the primary attack surface, not the control logic itself. One of the most underestimated cyber risks comes from engineering laptops, maintenance access ports, and software updates and configuration tools. These systems have high privileges, are used only occasionally, and may connect to external networks. Historically, many real-world cyber incidents entered industrial systems through engineering and maintenance access, not through operational control paths. HVDC systems present unique detection challenges, extremely fast dynamics, limited tolerance for false alarms, and complex interactions between control and protection. A cyber incident may look like a hardware failure, appear as control instability, or trigger protection without a clear root cause. This makes post-event analysis extremely difficult. It is important to be precise. HVDC systems are highly engineered, robust against physical disturbances, and designed with redundancy. But they are also sensitive to control integrity, dependent on correct data, and vulnerable to subtle manipulation. Cybersecurity in HVDC is about precision, not panic. HVDC converter stations are among the most complex assets in modern power systems. Their cyber risks do not come from a single weak point, but from the combination of digital control, communication dependency, centralized coordination, and human interaction during engineering and maintenance. Protecting HVDC systems starts with understanding where the risks actually exist, not where we assume they are.